Hi everyone, and welcome to today's seminar. It's Ocean's 161st International Seminar, and I'm Haeju, and I'll be moderating this session today. So we have Alicia with us today, who will be presenting a paper titled "On Estimation of the Abundance of Plastic Litter Generated by Beach Users Nationwide in Japan." So thank you, Alicia. The floor is yours.
Thank you, Heju. So today's paper actually is quite difficult. So I consulted ChatGPT for help, a lot of help. And there are probably things that is omitted from the original paper. So if you want to see the full paper, please refer to the paper. So this is the contents of today's presentation. First, I'll walk you through the abstract, then we'll go into the main contents of the paper, and then we will have Q&A and discussion. This is the abstract. Although the stock of plastic litter on beaches has been estimated in previous studies, knowledge gaps exist with regard to the amount of annually generated litter by beach users and the absence of litter generation rate. So if you notice, I've highlighted the LGR because we will keep seeing this LGR from here on forward. This study aimed to estimate beach-based litter by obtaining data from collected beach-based plastic litter, and then second, measurement of person hours of the users using regular photography and videography in summer or autumn-winter across 4 beaches in Japan. Additionally, in order to calculate the LGR estimates for the whole country, they use mobile phone big data to assess the person hours of users on 770 beaches. With the mobile phone big data, they then calculated the nationwide LGR and the estimated total litter abundance generated annually in Japan. So the main results of their paper is as follows. In summer, LGR ranged from 0.178 to 1.10 grams per person per hour. In autumn or winter, it was 0.128 to 0.453 grams per person per hour. LGR weight was on 0.1 order regardless of season and site, and it was also different based on season and seen to be higher in summer. Lastly, the estimated total abundance of litter generated by beach users nationwide in weight was 12.50 tons per year or 2.8 million items per year. So for the introduction, beaches are tourist assets, but hotspots for microplastic generation. The authors mentioned this because the authors mentioned microplastic because I think they want to have another paper, a second follow-up paper on microplastics. So they briefly mention it here, and then it just disappears from the rest of the paper. Additionally, the abundance of litter accumulated on beaches can be calculated based on the abundance of beach-based litter. This means the litter intentionally or unintentionally generated by beach users and the abundance of beach litter, which gets washed up ashore from the sea. So one of it is from land through beachgoers, and the other is from the sea. So to understand the mechanisms of litter generation by beach users, it is essential to evaluate the litter generation rate and establish correlations between the litter generation rate and the user's socio-economic background, duration of stay, behaviors of users on the beach, seasonality, and dependency of beach typology. The authors point out that the litter generation rate should be evaluated in terms of number, which is substantial for assessing the aesthetic impact, or 2, the mass, which is crucial for calculating plastic budget and potential microplastic generation in the marine environment. So most studies so far have focused on quantity of litter accumulated on beaches and their density across length or area. However, these studies do not explicitly distinguish between the abundance of beach-based litter and beach litter. So hence, the objectives of this study is first to measure the litter generation rate of four Japanese beaches during different seasons, use LGR and mobile phone big data to estimate total annual plastic litter generated by users nationwide, and provide a baseline method that others can replicate. There are 4 main study sites for this paper, and they were selected based on the number of users from 770 beaches in 2018. 3 of them were selected from the top 10 beaches, which are considerably impactful to the total litter discharge, whereas the final one beach, Futami Beach, was chosen because it is accessible to Ehime University, where the authors of this paper are mainly based at. Surveys were conducted during the high season in summer and low season in autumn-winter. I summarized the beach categorization into this table here. As you can see in the images, the beach types is different in terms of sand color and natural or man-made beaches. 2 of the beaches are based in Tokyo, which are accessible through public transport. So the authors categorize these 2 beaches as urban beaches, whereas Shirarahama and Futami are only accessible by automobile, so they are not urban beaches and therefore village or rural beaches. For Shirarahama Beach, this beach is located near a hot spring, so it's a tourist attraction site. And if you see in the image, in the image there, you can see that there's a lot of shops and huts that people open shops for economic purposes. And then for Futami, it is a rural area. The beach lengths are all different, with Yugaihama as the longest and Futami as the shortest length. One thing I noticed from the graph, figure 1 above there, is that 3 of the beaches are actually near a river. So I was actually curious if this would slightly influence the litter generation rate, but we can discuss this later. This river is actually not mentioned in the paper, so I don't know why they chose it. And then if you see table 1 here, as I've highlighted, the length of survey is different from the length of the beach. For Futami, it's 1-to-1 ratio. That means they do the survey in the whole beach, and then Yuigahama is 1/4, and then Zushi is 1/5, and Shirahama is 1/3. The reason for this difference is because it was determined by considering the number of surveyors, location, range, and the number of time-lapse cameras. Also taking into the account of non-uniformity of density of the number of users and the beach entrance locations. This is the steps that the authors did to collect the beach-generated litter and how they counted users. First, they carried out an initial cleanup before the survey to set baseline. Then they carry out hourly collection of new litter by walking along 5-meter space transects. Surveyors separated the new litter based on newly visible litter, litters previously generated, and cigarette butts. Thirdly, they did visual evaluation of litter age to exclude pre-existing beach litter such as biofilms, damage, or expiration dates. Then they calculated the beach users via time-lapse cameras, mobile phone videos, and visual tracing of 10 usage to estimate duration of stay. And then once they finish all their beach survey, they bring all the litter to the lab, where they then clean, dry, and weigh the litters before categorizing them based on material and usage behavior. I've summarized their material and usage behavior here, but if you want a more in-depth categorization, you can refer to their supplementary materials 1 and 2. Next, the number of beachgoers were quantified using visual analysis of photographs or videos of the survey areas with time-lapse cameras and mobile phones. The duration of data visualization visual data collection varied according to season and location. At some locations, video were prohibited, so surveyors could only manually count the number of beachgoers. In the paper, there are actually a lot of equations on how they calculated a lot of things, but the most important formula is this formula, which I included here, which is the litter generation rate formula. This formula is expressed by dividing the total generation litter based on the divided by the total person hours. This litter generation rate is calculated separately for each site and season using observed litter and user hours. If you're interested to know the other formulas, these are the other formulas that include the other formulas and explanations, such as the non-metric multi-dimensional scaling to analyze different LGR composition between the 4 sampling sites and 2 seasons, the estimated person hours of beach users at 770 beaches, estimated weight number of generated litter annually, and their error estimation. So if you are curious, you can take a look at the original paper. Now we move on to the results. Here, I put the overall results into this table. It is separated by summer and autumn winter. The total weight and number of collected items is almost or more than 10 times higher in summer compared to autumn winter. The average weight of each litter was 3.58 gram per item in autumn winter and 5.35 gram per item in summer. The larger variation in summer is due to higher user activities such as eating, drinking, and bathing. Also, cigarette butts dominated the item count, while tents, mats, and toys dominated by weight. So figure 2 illustrates user activity across different times of a day in summer and autumn winter. For summer, users peak around 3 p.m., while for winter, users peaked around after sunset hours. For the characteristics of beach-based litter, the dominant subcategories in terms of weight and items were completely different. In terms of season based on number, cigarette butts were dominant and accounted for up to 40% and 28%. Fragments were 12% and 14%. Food containers and wrappers were 16% and 12%, while bottles and caps were 9% and 11%. So these 4 major subcategories accounted for 75% in autumn, winter, and 66% in summer, indicating that litter is likely generated from smoking, eating, and drinking behaviors. For weight in autumn, fabrics was 50%, bottles and caps 13%, and others was 11%. In summer, toys were 20%, tents and mats were 18%, bottles and caps 16%, and fabrics 13%. These percentages accounted for 74% in autumn, winter, and 67% in summer. So if you compare both the number and weight, except for bottle caps, the dominant categories were completely different regardless of season. The characteristics of beach-based litter is as shown here. In terms of weight class number, the number of items in class less than 1 gram per item, including cigarette butts and most fragments, dominated regardless of season. Items in this weight class accounted for 59% in summer and 75% in autumn or winter. For weight class based on weight, items in the class 10 to 500 gram per item dominated both seasons, accounting for 78% in summer and 77% in autumn-winter. The average weight of items such as tents and mats, toys, and fabrics dominated the total weights in both seasons, exceeding those of other seasons. While items generated from bathing activities were much heavier than those originating from other activities. So in summary, for number, smoking and eating and drinking behaviors had major impact, whereas bathing significantly affected the weight. Moving to daytime accumulation rate density, these DARs are consistently higher in summer than autumn-winter across all units. Urban beaches like Yurikahama and Zushi had the highest daytime accumulation rate, possibly due to higher beach goer quantity, whereas rural beaches like Futami, which is on the rural area, had the lower accumulation rate. The daytime accumulation rate density were possibly relatively overestimated because films, fragments, and plastic bags were likely to be blown away on beaches during daytime. For the litter generation rate based on seasonality, the summer LGR was 0.733 gram per person per hour and 0.137 items per person per hour, while autumn-winter, the average was 0.28 grams per person per hour and 0.078 items per person per hour. And as shown in Table 4 and highlighted in pink, the urban beaches had higher LGR in summer regardless of weight and quantity. So you will notice throughout the whole paper, they will keep bringing up the point of summer being the higher point. And then for litter density, diversity, and similarity, there were more litter categories observed in summer compared to autumn-winter, but summer litter patterns were more similar across beaches as shown in Figure 9. The litter categories in winter were more varied due to fewer and more random litter items. Here is the nationwide estimates based on total weight and number of annually generated litter. The authors calculated the statistical litter generation rate, which I've omitted in this presentation, but you can refer to in Table 5 of the paper. The average LGR weighted by number of beach users range from 0.280 to 0.54 grams per person per hour and from 0.078 to 0.117 items per person per hour. Based on person hours and LGR, the estimated litter from 770 beaches were 12.50 tons per year and 2.8 million items per year. Summer, unsurprisingly, accounted for more than half of the total litter, and urban beaches near Tokyo and Osaka were key contributors. Considering that many of us here have also been involved with our own national beach litter monitoring programs, I will be curious to hear your opinions or experiences if these results of summer and urban beaches are also the highest in your own home countries or surveys. But before we can go into that discussion, let's go into the discussion from this paper. There are 5 main points of the paper's discussion. The first is LGR as a useful metric. So LGR in both weight and number offers a standardized measure of litter pressure. Also, it also allows comparison across different seasons, locations, and countries. In this study, the authors demonstrated that LGR are consistently higher in summer, and it is relatively stable across sites, meaning they can be scaled up nationally with some confidence. Secondly, there is a significant difference between seasonality and urban versus rural beaches. Summer LGRs were 2.6 times higher in terms of weight and 1.8 times higher in terms of items compared to winter. Urban beaches had significantly higher LGRs in summer due to higher population density and more varied activities such as eating, drinking, and bathing, playing. In winter, the difference between urban and rural beaches disappeared, suggesting that tourism concentration is a key drive. Third, litter composition is shaped by user behavior. Behavior categories like bathing, smoking, eating, drinking produce different types of litter. For example, smoking generated smaller yet larger amounts of litter, whereas bathing had fewer but much heavier and larger items. By understanding behavior-linked litter types, this can inform targeted interventions like banning smoking on beaches completely. Fourth, there is a significance of usage of tents and mats. Despite being used only by a minority of users, tents and mats significantly contributed to total litter weight. This suggests that even low-frequency, high-impact items matter and should be considered in waste prevention campaigns. Finally, LGR differences between sites were not very large compared to other environmental variables such as wave conditions. This low variability supports the idea that national LGR estimates are robust, even if only a few representative beaches are surveyed. In the conclusion of this paper, their first conclusion is that this results is the first national estimate of user-generated beach litter in Japan, combining empirical data collection with mobile phone big data. They also provide both weight and item-based litter abundance estimates, which are the proposed baseline values for future monitoring and comparisons. Additionally, summer was the most critical season, contributing to over 50% of annual litter, indicating a strong need for seasonality targeted policies and cleanup efforts. And finally, urban beaches are hotspots due to higher user density, accessibility, and longer visits. This is the final slide. The above is the limitations that the authors pointed out, such as exclusion of nighttime littering events, illegal dumping or non-bathing of off-season beaches. It also included other materials such as metal, foam, and glass. And also this study was carried out after their morning cleaning, which might underestimate the original microplastic abundance or litter generation rate. And below are some discussion questions that I think that we can discuss together. That's all. Thank you.